So I'll get on with the isotope synthesis. I guess first things first, we are grateful for the funding from the Canada First Research Excellence Fund, as well as all the partners with Metal Earth that has made all this possible. This project is kind of something that was designed for me coming out of my PhD. I basically just got to continue my PhD, and I can say now that confidently it's done. So zircon crystallization ages date events, whereas model ages estimate the source history. Both of these things are pretty important to reconstruct how and when continental crust formed, was modified, and or recycled. So for zircon hafnium model ages, the protolith's time-integrated evolution must either be assumed or prior knowledge is required. In contrast, for whole rock neodymium, you take one measurement and you calculate the model age from that. So we actually developed a new depleted mantle model for hafnium isotopes, partly to address the Superior Province and also partly to deal with some issues in the Grenville Province. So other depleted mantle models for hafnium are typically too depleted and yield model ages that are too old, as in the DM model on the right, used by Slagstad et al., or also in the Eoarchean and Proterozoic. So our depleted mantle model generates hafnium model ages for Archean to Mesoproterozoic TTG gneisses in the Grenville Province that are consistent with their whole rock neodymium model ages. And since the Grenville Province contains Archean crusts derived from the Superior Province, I'm also able to apply this model to the Superior Province. So there's a variety of models. There's the new crust model by Dweem, which is this tiny dotted line. There's the model by Vervoort and Kemp, 2025, which is this dashed line. And then there's this old Griffin et al. 2002 model in the gray line. This Griffin et al. Model is similar to the Slagstad et al. Model. You can see it's well above the, you're not going to get any indication of juvenile crustal growth using that curve because all juvenile crust is down here. We're not using the Vervoort and Kemp 2025 model because that model doesn't account for Eoarchean gneisses in Greenland, which are slightly superchondritic. The next best model is the Dweem et al. Model, the new crust model, which is fairly accurate for estimated crustal formation ages in the Archean and Proterozoic. But our model is characterized for Archean and Proterozoic crust in the Grenville Province, which have been analyzed by and characterized by whole rock neodymium isotopes. So this is the sample distribution. The zircon, hafnium, and whole rock neodymium samples cover about 75% of the Superior Province. The whole rock neodymium data is kind of unevenly distributed, making it sort of just a comparison to the zircon hafnium data that we have. And the highest concentration of data is in the Abitibi, courtesy of David Mole and Christine Nguyen. So these are the compilation of zircon uranium lead ages. The Abitibi is no surprise. The Abitibi and Wawa terrains contain the greatest concentration of Neo-Archean crust. And we'll also point out that Western Wabigoon has a concentration of Neo-Archean crust near the center of it. But overall, the Western Superior Province has significantly more Mesoarchean crust in addition to the older Eoto-Paleoarchean remnants in the Hudson Bay terrain, Winnipeg River terrain, and Minnesota River Valley terrain. So the KDE shows there's a major mode at 2.71, which is dominated by samples in the Abitibi and Wawa. But it's important to recognize the presence of Mesoarchean crust and an inheritance in the Abitibi and Wawa terrains, but also the difference in concentration and volume. So these are the zircon hafnium depleted mantle model depleted mantle model ages, which have been interpolated using kriging, and we've applied a mask using interpolated errors greater than 130. So any interpolated errors greater than 130, we've cut those out just to give you the highest confidence interpolation map. And what you can see is that there's a general west-east gradation or east-west gradation from evolved crust in the west to juvenile crust in the east, where Wawa and West Wabagoon are sort of transitional between the older North Caribou terrain and the much more juvenile Abitibi terrain. So the zircon hafnium model age, KDE, has two main modes at 2.74 and 2.98, which represent the major crustal formation events in the Superior Province. There's some other older events, but these are drowned out in the compilation with modes at 3.17, 3.25, 3.39, et cetera. And these also correlate with general magmatic ages as well. So in the epsilon hafnium plot here, each sample represents a weighted average of a zircon population. So either a xenocristic population or a main igneous population. And beginning with the three older gneiss strains, there's clear overlap, as I've already mentioned, and highlighted by these gray bars. And this is a close-up on the Meso to Neo-Archean. And what we see are the three major magmatic events, which are recorded in the KDE, 3.0 to 2.9, 2.85, and 2.75 to 2.7, which represent the most prevalent crust in the Superior Province. And so one of the interesting aspects of producing this compilation was that I ended up finding that the Abitibi, Wawa, Opatica, and Eastern Wabagoon, Western Wabagoon, and North Caribou terrains actually all have some sort of overlap in magmatic age or isotope composition. And if we follow these evolution lines down here, we see there's North Caribou terrain, Pontiac, Wawa, West Wabagoon, and they're all sort of plodding along this evolution trend, indicating that there's older Paleoarchean, late Paleoarchean crusts preserved or at least being assimilated in these terrains. The other thing that we find is that this 3.0 to 2.9 juvenile crust produced in the North Caribou terrain, there's a xenocrist there from West Wabagoon, and then the Wawa data from the Hawk assemblage also plots along this evolution line, indicating that this is essentially just deriving similar, is reworking similar crust as found in the North Caribou terrain. And then lo and behold, there you've got a little Abitibi xenocrist plotting along the same evolutionary trend. And this is one of the younger xenocrysts in Abitibi. There's actually 2.9 as well as a 3.0 dated xenocryst by Wood and Clayton in 1985, and then Berry and Davis in 1992. And those don't have hafnium composition. So depending on what their hafnium composition shows for those samples, they probably end up just plotting along this trend, right? This is basically a trend that you should pick up anywhere you sample in the Superior Province. I would argue. So prior to 3 billion years, crustal residence times were greater than 100 million years during the three major magmatic events. Prior to 3GA, crustal residence times were greater than 100 million years. During the three major magmatic events in the Superior Province, however, crustal residence times ranged from 450 down to essentially zero, which shows that juvenile crustal growth in the Superior Province occurred in association with older Paleo to Mesoarchean crust. And this is just another way to show that plot in log form, which highlights, these three episodes of juvenile or semi-juvenile crustal growth at 2.75 to 2.7, 2.85 to 2.8, 2.85 is mostly reworking though, and then 3.0 to 2.9. So these are where juvenile crust is being created in the Superior Province. And before that, we don't really have much true juvenile crust. So now moving on to the whole rock neodymium model ages, there's a limited difference from the zircon data, but we've got additional data in the northeastern Superior Province, which allow us to draw some correlations potentially with the North Caribou terrain over here, because it's very similar in composition as well as age. So the KDE for the whole rock model ages, modes are pretty similar as the zircon hafnium, showing that the two isotope systems yield consistent results. However, there is a prominent mode at 2.84 in the whole rock neodymium data, which is only a minor unlabeled mode in the zircon hafnium isotope data, which may in part be derived from greater sensitivity of the whole rock neodymium isotope system to crustal assimilation between juvenile Neo-Archean and older Mesoarchean sources. So this is a comparison of the Western, a subset of data from the Western Superior Province, outlined in the black box there. And I've made KDEs for both the whole rock neodymium and the zircon hafnium, and what you find is that there's essentially exact overlap between them, except for we're missing a Neo-Archean peak here, which again is probably a result of the greater sensitivity of the neodymium isotope system to crustal assimilation. But we find there's, 2740, 2720, 2990, 2990, 3180, 3168, 3250, 3260. They match basically bang on. And so that's indicating that the depleted mantle model for neodymium is essentially equivalent to the depleted mantle model for hafnium that we developed. And so this is just another comparison highlighting that, so this is from Henry et al. 2000, where they've done whole rock neodymium as well as zircon uranium lead dating. And what you find is that they found the exact same pattern with whole rock neodymium data that we found with the zircon hafnium data. And so this just shows that, we've done some hard science. When you do hard science, it comes out the same every time. It doesn't matter what you do. And so this is the final sort of synthesis of all that data. You'll notice there's a problem here. I'm missing a scale bar for the interpolation, but this will be similar to this scale bar. And you'll also notice a problem with this scale bar, which is I haven't actually labeled the major colors in here. So yellow, what is that? We've only got a range of 1.4 billion years. So I've got to do some detailing in these figures. But so the interpolated zircon hafnium depleted mantle model ages for the Superior Province show a general east-west or west-east gradient from evolved crusts in the west to younger juvenile crust in the east. The symbols indicate VMS deposits, nickel, copper, platinum group deposits, and LCT pegmatites. And what you can see is that, you get away from the Abitibi, you find LCT pegmatites. You move into the Abitibi, you find VMS deposits, nickel, copper, and platinum group. I'm assuming that this is related to the fertility of the crust in the Abitibi. It's more juvenile, it's more fertile, and so you'll probably see something similar when it comes to orogenic gold. I haven't included orogenic gold because there's sort of a couple stages of processes that you have to do to get to producing orogenic gold. For example, as Bruno showed, it's quite late in the Superior Province. Whereas these VMS deposits, LCT pegmatites, even though they're late, and nickel, copper, platinum group, they're more related to actual magmatic phases rather than later metamorphic evolution. So in order to interpret all this data, I've come up with sort of a new way to look at it. I've put lipstick on a pig, I guess you could say. But I've come up with this idea of metallogenic terrain types, which fall on some sort of a continuum. So on one hand, you have Abitibi type, which are dominated almost entirely by Neo-Archean crust. There's limited crustal assimilation, although there's some xenocrysts. Geochemistry shows limited crustal assimilation. Crust is isotopically depleted. I say here it's thinner, but I wouldn't say it's thinner. It's sort of thinner maybe, but more variable. And then, of course, you've got these VMS, nickel, copper, and a lack of LCT pegmatites. And then on the other hand of the continuum, you have North Caribou type metallogenic terrains, which contain Meso to Neo-Archean crusts, remnants of older crusts. The Neo-Archean crust in the North Caribou terrain is generally less isotopically depleted. It also often contains xenocrystic zircon populations associated with reworked and juvenile Mesoarchean crust. There's significant crustal assimilation in terms of geochemistry in North Caribou terrain. There's generally thicker crust, but maybe thicker isn't the best word, maybe the sort of thicker and less variable. There's limited VMS, nickel, copper, platinum group, except for Uchi might be a bit of an exception. There's some orogenic gold, some intrusion-related gold, but there's several LCT pegmatite fields. And so the thing about LCT pegmatites is that there's no real reason why they shouldn't be in Abitibi, but I have a feeling that this is in part related to the fact that the crust is older, it's able to stew a little bit more, metasomatize, and because it's slightly thicker and less variable, its biotite breakdown is more efficient, allowing the expulsion of lithium into metamorphic fluids, which can then form these LCT pegmatites. There's currently two sort of contrasting models for the production of LCT pegmatites. One of them involves metasedimentary rocks, which it makes sense why we find a bunch of LCT pegmatites in Quetico and English River, but there's not really much of an explanation for why we find these sort of somewhat large LCT pegmatites in the North Caribou terrain, which generally does not have metasedimentary rocks at depth and has much more limited perluminous granites. And so that's that one.